Okay, so our first application here is going to be our incline problems, and it's going to deal with moving weights up inclines, which could be a ramp of some sort or it could be just a cross section of a hill. We are not taking into consideration what the ramp is made up of. Obviously, if this was an ice ramp, it would take a little less force than if this was asphalt or a gravel ramp. So this is kind of just in a scientific lab. Hey, let's look at the vectors required and the forces required to overcome and get this thing to move up the hill. All right, so the first force that we're going to talk about is just the force that's required to pull this thing up the hill. And this force is the one where we're going to be solving for. This force, kind of the key components, is that it's going to be parallel to the ramp itself. And this is kind of like the equilibrium force to keep this weight stationary. We'd actually need to apply more force than this to get it to move up the hill. This amount of force actually just keeps it still or keeps it from sliding backwards, overcoming the incline or the slope. All right, so we generally represent that vector kind of right there, parallel to the hill. That's the one that's being applied to the weight itself. The other vector, we obviously know that gravity is involved with this thing, and the gravity vector is always perpendicular to the center of the earth, or perpendicular to the horizontal. So we actually do get another right angle of form right here. All right, that one's always going straight down on paper towards the center of the earth, or perpendicular to the horizontal if you're looking at a cross section of something. So that's going to be our gravity force. The final force is the friction force, and there's a friction force that happens between the ramp and the weight itself. The friction force is always going to be applied perpendicularly to the ramp. Okay? So in this case, we will have another right angle that's formed right here. All right? And what we would take a look at and set up and do is that this relationship between these three vectors is always kind of this situation here. So I'm going to leave that vector there actually. I'll grab another one. But if you notice, those three vectors make a nice little triangle. So what we look at setting up and looking at here is that the gravity vector and the force required to keep that weight from sliding down the hill, their resultant is friction. Okay? So the resultant of gravity and the force required is the friction force, and that relationship is always maintained throughout these problems, throughout these incline problems, and knowing that, we can kind of set up this triangle here and solve for any one of those pieces. Okay. The one other piece of information that we need to remember about the gravity force is that its magnitude is always equal to the weight of the object. So the magnitude of our gravity here is going to be 50. We'll know that, or we'll be able to find that. The other relationships, the other key pieces of information here is that this angle is going to be a right angle because we know that this vector would be parallel with itself. Okay? And these would be alternate interior angles if we considered this a transversal. So that's going to be a 90. And the one other last little piece of information we need to know about these setups is that the angle of the incline is actually the angle that would exist between gravity and friction. So that incline angle there, or the angle between those two vectors, is always equal to the incline of the ramp. And with that setup, we actually have a right triangle. We might not necessarily need our law of sines and law of cosines. So let's take a look at an example here. Just remember those three vectors and how they interact with each other, and we'll set up the next problem to solve it through. So here we go. The example that we're going to look at says find the force required to pull a 50-pound weight up a ramp inclined at 20 degrees to the horizontal. So we got a 50-pound weight. We know that. It also tells us the incline of the ramp is 20 degrees. Okay. And then we got to set up our forces and fill in what we know, and we're trying to figure out that force required. So that's that bottom force that's parallel to the ramp itself. So let's draw in our three vectors. We have gravity pulling straight down towards the center of the earth, okay, and we know that that magnitude is equal to the weight itself. So that one has a magnitude of 50. We have our friction force. Okay, remember that one's perpendicular to the ramp, and we don't know the magnitude of that one at this point. And then we also have our third vector, which is the force required to keep that thing stationary or force to overcome to get it to come up the hill. And that one, if we go tail the tip with gravity, that one forms, or the resultant of those two should form friction. Okay, so we know then, hey, right angle here, those two have a right angle, these two have a right angle, and with that setup, we should be able to find this value right here. Let's call this magnitude of V. That's what we're looking for. The force required to keep this thing from sliding down the hill or moved up the ramp. And the one other piece, the incline of the ramp, is the same as the angle between friction and gravity's force. So that's a 20-degree angle right there. And with that, we do have a right triangle, so we have SOHCAHTOA. We don't need law of sines or law of cosines. This is just a pretty quick setup. And again, as long as we know one of these three sides, we can find any of the other missing ones. So we're going to set up a trig function from our 20-degree angle here that deals with magnitude of V, unknown, and this would be our hypotenuse. So this looks like opposite, and this is our hypotenuse. So with that setup, that sounds like sine to me. So if we go ahead and write a sine function, sine of 20 degrees should be equal to the magnitude of V over 50, the size of the hypotenuse. And if we just multiply both sides by 50 here, we get 50 times the sine of 20 equals magnitude of V, and that should again solve for that force that they're looking for, the force required here. So if we turn our calculator on, let's punch this in. 50 times the sine, let me check my mode here real quick, good, I'm in degrees, times the sine of 20 degrees, hit enter, and there it is. So the magnitude or the force required to keep this weight stationary would be 17.1 pounds, it looks like, pounds is our unit. Now again, to overcome, to get this thing to slide up the hill, we would need to apply more force than that just to keep it where it is. We would apply that exact amount of force. So, all right. So with that, go ahead and try the example problems. Again, just keep in mind the relationships there. Angle of the incline is the angle between friction and gravity. The force required and gravity vector, their resultant should form friction vector. There's a right angle between those two, and that one's always straight down, that one's perpendicular to the ramp, and that one's parallel to the ramp, the force required. So good luck, hope that helps. Ask questions if you got them.